Okay, welcome back. This is Mr. Hassan's Maths channel, and I'm now answering question number 4 from the January 2020 International A-Level Edexcel Statistics S1 paper. In this question here, we've got a frequency table. It says a researcher is studying the birth weights of babies. A random sample of 98 babies was taken, and their birth weight in kilograms, W kilograms, are summarized in the table below. So you've got the birth weights in groups, the frequencies for each of the categories there, each of the groups, the number of babies who have weights between those values, basically. And you've also got what's called the midpoint of each of these categories, given in this column over there. And they've also told us what the sum of fx is, the sum of this times this, plus this times this, this times this, this times this, this times this, the sum of those, fx, the sum of f times x. And they've also told us what the sum of f times x squared is, which is going to be basically the frequency times the square. So 16 times 4, 24 times 2.75 squared, 32 times 3.25 squared, so on. The sum of all of that they're given here. Those are useful for finding the mean and also the standard deviation, which I guess is going to be asked. Then it says a histogram is drawn to represent these data. The bar representing the birth weight 1.5 to 2.5 has a width of 1 centimeter and a height of 4 centimeters. We've got to calculate the width and height of the bar representing the birth weight of 3.5 to 4. Okay, so we've got to focus on these two. Okay, and we know we've got to find these two. Those are what we've got to focus on. Now we know the details of this. That's what we've got to find. So what I'm going to do is I'm going to say, okay, let's look at the group 3.5 to 4. And we have to also consider the group 1.5 to 2.5. Okay, those are the two groups we have to consider. And we have to find the width and also the height of both of those. Okay, now, what determines the width of the bar? Well, the class width. Okay, the class width determines the width of the bar, how many centimeters it's going to be. And we know for the 1.5 to 2.5 category, the width is 1 centimeter. And that represents a class width of, as we can see, 1. 2.5 minus 1.5 is 1. So 1 centimeter represents 1 unit of class width. All right, and so we can say that the width of this bar, W centimeters, is going to be represented by the width of this class, which is 0.5. So we can say straight away that the width of what we're looking for is going to be 0.5 centimeters. Okay, now what is it that determines the height of the bar in a histogram? All right. Well, it is not the frequency, but it's the frequency density. So we got to look for the frequency density. Now, the frequency density is equal to the frequency divided by the interval. So here we have 16 divided by 1, which is 16. And here we have 14 divided by 0.5. So you have 14, so this is 16 divided by 1, which is 16. And here we have 14 divided by 0.5. Now that's 14 multiplied by 2, which is 28. So 28 is the frequency density of this one that we have to find. So the one that we have to find, its height is representing 28 centimeters of frequency density. And then the one that we already know the height of, which is 4 centimeters, we can say 4 centimeters of height is representing a frequency density of 16 centimeters. Okay, because the height is representative of the frequency density. All right, not the frequency. So here we can find what h is. We can just do a simple cross multiplication. It's 4 times 28 divided by 16. That cancels with that, leaving you with 4. That cancels with that, giving you 7 centimeters. So we can say that the width is 0.5 centimeters and the height is equal to 7 centimeters. Okay, this is a typical question in histograms where they tell you the dimensions of one bar, and you have to use that to find the dimensions of another bar. Okay, and you use the fact that the width of the bars is determined by the width of the interval, and the height of the bar is determined by the frequency density. Okay, so that's the key to answering such questions. So that's part A done. Now for part B, it says use linear interpolation to estimate the lower quartile of the birth weights of the 98 babies. So we have 98 entries, so 98 divided by 4, okay, is going to give us the position of, we're looking for the position of Q1 first. The position of Q1, which is the lower quartile. The lower quartile is Q1. So the position is 98 divided by 4. So 98 divided by 4 gives us 24.5. So it's the 24.5th position. Now we don't round up and say, okay, it's the 25th entry. No, because we have grouped data here. So we take 24.5 as it is. All right, and now we're going to use linear interpolation to figure out what we're going to find. So we're looking for, this is the value on the top. I like to make my linear interpolation like this, with the value on the top and the position underneath, because I'm trying to find a value. So we're looking for Q1, which is the lower quartile, and I know that that's the 24.5th position. Right now, Q1 is going to be in which group? Okay, well, if you look at the groups, the 24.5th position is going to be in this group over here, because you've got 16 entries in the first group, and then the next 24 entries are in the second group. So the 24.5th entry is going to be somewhere in this group here. So the beginning of the group is 2.5, 2.50. The end of the group is 3.5, 2.5 to 3.5 in that group. Oh, sorry, to 3, not 3.5. Be careful there. 2.5 to 3. Yeah, that's the group that it's in. And in the beginning of that group, you're on the 16th position. So in the beginning of the group, you're on the 16th position. Then you got 14 positions in this group. So by the end of the group, you got 24 positions in that group. 24 basically entries in that group. So you got 16 plus 24, which is 40. By the end of the group, you're on the 40th position. So what we can do is you can use some proportion here to find what Q1 is. I know that Q1 is equal to 2.5. I know it's more than 2.5. Plus, now I need to work out what this distance is, okay, in terms of the value. Well, I know the fraction that this makes with that, and that width here is 0.5, is equal to the same fraction that this position 24.5 makes along this group. Okay, so I know that this distance here, 24.5 minus 16, divided by the total width of this group, 24, that fraction, this fraction of this section here is equal to the same fraction that this makes with that group there. So I can say that this fraction of this width, 0.5, is going to give us how far into the group it is. So 2.5 plus the distance here, which is that's going to be 8.5 over 24 times 0.5. That will give us what Q1 is. So you got 2.5 plus, and you're going to have 24.5 minus 16. So that's how far into the group you are in terms of the position, divided by the width of the group in terms of the position. That fraction of the width of the group, which is 0.5, in terms of the value. What's going on there? In terms of the value, that will give you the value of Q1. So you get 2.6770, 2.677083 continues on. So we want to round it to 3SF. It didn't tell us how to round it, so we should give it to 3SF if it's not stated. So we can say Q1 therefore is 2.68. Okay, 2.68 kilograms. That's the value of Q1. Okay. Yeah. So that is the birth, that is the lower quartile of the birth weights. All right. Then it says the researcher estimated the median to be 3.14. So the median is Q2, 3.14 kilograms. And the upper quartile, Q3, is estimated to be 3.55 kilograms. And we've just worked out Q1 is equal to 2.68 kilograms. So we got to use the median and the quartiles to describe the skewness of these data. So basically, if we remember box and whisker plots, it's a nice, easy way to understand this. If you think about box and whisker plot and the box part of it, okay, in the box part of the box and whisker plots, what you have is you have your upper quartile, the top, the right side, the lower quartile on the left side, and in between them you have the median. Okay, so you have, this is Q1, this is Q2, and this is Q2, this is Q3. Okay, so you have the lower quartile, the median, and the upper quartile. All right, now if this line is closer to there, okay, that means that, what happened here? Let's do this. Okay, that means, so if the median is closer to the lower quartile than the upper quartile, that means that 25% of the data, remember each of these, between each of these, there's 25% of the data. 25% of the data is, you know, within a smaller kind of range. So it's more concentrated on this side. So if you drew the frequency table or something like that, it will look something like this. If you were to draw the histogram, something like that, it will have positive skew. But if Q2 is closer to Q3, then you can say that the 25% of the data is concentrated in a smaller range, and so it will have this type of shape. It will be negative skew, more skew towards the higher values. All right. So depending on the difference between Q2 and Q1, you can work out whether it's got positive or negative skew. All right. So let's work out what Q2 minus Q1 is. So we've got Q2 minus Q1. And let's work out what Q3 minus Q2 is, and that will help us determine whether it's positive or negative skew. So Q2 minus Q1 is 3.14 minus 2.68, and Q3 minus Q2 is going to be 3.55 minus 3.14. And let's see what we get. So we have 3.14 take away 2.68. That gives us 0.46. And then we have Q3 minus Q2, which is 3.55. Take away 3.14. That gives us 0.41. So we can say that if we justify this by saying that as I'm doing something which I shouldn't really do, but I'm going to continue down here. Okay, really should go to the next page. I'll just stick it in here. As Q, you can say as Q2 minus Q1 is greater than Q3 minus Q2 minus Q2. Q3 minus Q2. Now that means that Q2 minus Q1, so it's kind of like this kind of situation here, where you have negative skew, because Q2 minus Q1 is greater than Q3 minus Q2. All right, so that means the median is closer to the upper quartile than the lower quartile. Okay, so you could write that in words if you want. You could say, for example, Q2 is closer to Q3 than to Q1. Therefore, we have negative skew. Okay, so really I should have done this question on the other page, but it's done now. So as it looks like this, it's not too skewed, because it's kind of like they're not far away from each other, but yeah, it is negative skew. All right, so that's the answer here for part C of this question. All right, now because point 4 in the a grand scheme of things, is quite big actually. All right, 0.04, 0.46 or 0.05. It's not, a small amount if you compare it to what we're looking at here. Okay, so I don't think we should say it's very little skew, because it's 0.05 is quite a big number when you're looking at what we're comparing here. All right, so I think saying negative skew would be probably the best thing. I guess if somebody did try to justify and say it is like there is little skew, very little skew, I suppose that they could justify it by saying that the difference between Q2 and Q1 and Q3 and Q2 is not so big. They will still probably get the mark for that, because they justified it according to their values. That should be okay. Although I would stick with negative skew really, because as I said, these values are quite not so big, the difference between these limits here. And you can see that 0.05 will be kind of a significant difference in this particular case. So I think it's best to stick with negative skew in this case. Okay, now for part D. It says find an estimate for the mean birth weight and the standard deviation of the birth weights. Okay, so we've got to find the mean and the standard deviation from this frequency table. Now normally what we'd have to do to find the mean is we'd have to find fx, and to find the standard deviation we'd have to find fx squared. So we'd have to do 16 times the midpoint, which they've given us. X is the midpoint of each of these. And we'll multiply them and then add those together and then find the sum of fx. But they already gave us that here. So the sum of fx here, which we need to use to find the mean, is already given. And the fx squared is already given also. The sum of all the fx is here. And the sum of all the fx squared is already given to us. So we don't need to calculate that. Okay, so always look out for this information, because a lot of students sometimes they don't look at what's given and they kind of like start doing all this calculation and waste a lot of time. It's only worth 3 marks, and most of the work has already been done for you. Okay, so it's an estimate. Just a little background. The reason why it's an estimate is because we don't know the weight of each of these babies. We know there's 16 babies between these weights. We don't know the actual weights, so we have to estimate. Say 16 babies, we don't know what their weight is, somewhere between these two weights, so we take the mid-interval value. That's why it says birth weight midpoint. Take what's halfway between these two intervals. Okay, so we're going to have between 1.5 and 2.5 is 2, so we say, let's assume that those 16 babies have this weight. So 16 times 2 will give you the sum of the weights of those 16 babies, and you do the same for each of these categories. Look at the midpoints of these intervals, and then multiply them together. That gives you, if you add them together, the sum, an estimated sum of the weights of all the babies. Then you divide it by the number of babies, and they told us that there are 96 babies or 98 babies. 98 babies. So there's 98 babies altogether, so we know that the total is 98 here. All right, so we can say that the mean, okay, which is given the symbol mu, is equal to, you can also given the symbol W bar, you could call it, is equal to, an estimate of the mean, is equal to the sum of fx divided by the number of entries, which is 311.5 divided by 98, and that should give us the mean weight. So 311.5 divided by 98, that gives us 3.17857. 3.17857, which we'll say is 3.18 kilograms. That's the mean weight of those babies. And the standard deviation, which is given the symbol sigma, is equal to the square root of the variance. Now the variance is given by the mean of the squares minus the square of the mean. The mean of the squares is basically the sum of fx squared divided by the number of entries. So it's going to be, so I'll just write this here, it's the sum of fx squared divided by the number of entries minus the mean squared, So you're going to have basically the sum of fx squared, which is 1 1501.125 divided by the number of entries, the square root of all this, that's standard deviation is the square root of the variance, minus the square of the mean. Now I'm not going to use this value. I'm going to use the fraction that I had in the beginning before I rounded the answer. So I'll use 311.5 over 98 squared. I'll use that to calculate, since that's going to give me a more exact value than using this rounded mean. So I won't put 3.18 squared. I'll use a fraction that I used to get that answer before I rounded it, and that will give me a more accurate value of the standard deviation. So the standard deviation therefore is going to be equal to, I just have to stick this in my calculator now. So I'm going to have the square root of 1051.125 over 98. That's the mean of the squares, minus the square of the mean. So I'll put this in a bracket. I have 311.5 over 98, and that has to be squared. So the square, that's the mean of the squares minus the square of the mean, taking the square root of that, and that gives me, what have I done wrong here? Oh, I haven't done anything wrong here, that's fine. Just making sure. Yeah, everything's all right. So that gives me 0.78895. 0.78895 ... So that means therefore the standard deviation is equal to, I can't draw that very well, 0.7893 SF. So that's the standard deviation in kilograms for this data. That's part D done. Okay, now for part E, it says use the formula. Skewness is 3 times the mean minus the median over the standard deviation to estimate a value for the skewness of the data. So the mean, we found its estimated value to be 3.18. So I'll just use the rounded values here, 3.18. The median, Q2, I think that was already given to us in the last part of the question. The median, Q2, was 3.14. They gave it to us already. Okay, so 3.14 is the median. And the standard deviation, we just calculated it now to be 0.789. Okay, so we got to find the skewness. We can say the skewness of the data is 3 times the mean, 3.18, minus the median, which is 3.14, over the standard deviation, which is 0.789. Okay, the mean minus the median over the standard deviation, okay. Let's just make sure I wrote the right number down. So you have 3.14, that's right, median. Okay, so now we can calculate the skewness. That's going to give us, according to this criteria, the skewness is going to be 3 times 3.18 minus 3.14 divided by 0.789. Okay, just make sure we get it right there. Yep, and that's going to give us 0.152. 0.152. I'll just write it what it was before we rounded it. 9 ... So that's equal to 0.152. That's the skewness of the data. Give you answer to 2 significant figures, sorry. So 0.15. 0.15 is the skewness according to this criteria here. Okay, so that's part E. Now for part F. Part F tells us the researcher read the birth weights should be approximately normally distributed and decides to split the class 3 to 3.5. So wants to split up the class 3 to 3.5. The frequency for 3 to 3.25 is 9. So split this group up into 2 different parts. So what I'm going to do is I'm going to try to get rid of this and change it. So this part has now been replaced with another split into two columns. So this has now become two different categories. So I'll split this into two different categories. Okay, so what I'll do here is I'll make a new line and split it up. Okay, so now we have the two categories are now from 3 to 3.25. So oops, need to get the right color back. So I have 3.25. Right, 3 to 3.25. 3.25, and then you have from 3.25 W to 3.5. Okay, and the frequency for 3 to 3.25 is 9, and the frequency for this is 23. All right, so now, therefore the midpoint here is going to be 3.125, and the midpoint here is going to be 3.5. What's this? 3.5 plus 3.25 divided by 2 gives you 3.375. That will be the midpoint now, 375. Although I don't think we need that. It says state giving a reason. What effect would be on the estimate of the median? Okay, now, what effect will be on the effect of the median? Now, Q2, there's still 98 entries. He's just taken those 32 that were before in this group and split them into two separate groups. So the position of Q2, let's see what happens to the position of Q2 now. The position of Q2 is going to be, as we said, 98 divided by 2. Okay, so you have 98 divided by 2 is the position of Q2. So that is 49. So it's the 49th position. Now, in which group is the 49th position? You've got 16 plus 24 plus 9. That's 16. That's 40. Yeah, if you add those together, and that's 49. So it's going to be basically halfway between these two. Okay, so it's going to be, you can say, it's going to be 3.25. Okay, so the position of Q2 is now the 49th position, okay, which is 3.25. Now it's 3.25. So the position of Q2 is 3.25, okay. That will be the value of Q2. So Q2 is now 3.25, okay, because you can see it's right on the border. Previously, Q2 was 3.14, okay, so therefore you can say that Q2 is going to increase, okay. Q2 is going to increase because now it's in, a group which is further along than the group it was in before. Okay, before it was in the third group, now it's in the fourth group. Okay, before it was in the group here, it was in this group. Now it's been pushed along further into the next group. So you can say that the Q2, as you can see here, has increased. It's become 3.14. So Q2 increases, and then we got to, it says, without carrying out any further calculations, state giving a reason what the effect of this change would be on the estimate of the mean. Okay, so now what we're going to have here, if we estimate the mean, we're going to, before we would have 32 times the midpoint. Now we're going to have these two more categories here. Okay, so Q2 increases. Why does it increase? Because it is now in, you could say, the next group along. We worked out it increases. It is now 3.25. Okay, so, okay, increases to 3.25, we can say. Then we can now, that's part one. Then for part two, without carrying out any further calculation, state giving a reason what the effect of this change would be on the estimate of the mean. Well, basically, before we had 32 multiplied by the midpoint of these two, okay, which would have been 32 times 3.25. Now we've got 9 times 3.125 and 23 times 3.7375. So we can say that, you're going to have, a bigger number multiplied by a higher midpoint. Okay, so you can say that the value of the midpoint increases for most entries. Okay, so now you got 23 more values multiplied by a higher midpoint, okay, added to, less values multiplied by a lower midpoint. So therefore the mean is going to increase. Therefore the mean is going to increase. Okay, without doing a calculation, you can see that, because before the midpoint was 3 point, is between 3 and 3.5, 3.25. Okay, that was the mean. So you'd have 32 times 3.25. Now 9 of those values are multiplied by a lower value, but 23 of them are multiplied by a higher value, 3.375. So therefore the mean is going to increase. So if you mention that the value of the midpoint increases for most of the entries in that group, therefore the mean will increase, that's enough. It's only worth basically 1 mark. So you don't want to go into too much detail, that's fine. Okay, so that answers this question, part F, and that concludes question number 4 from January 2020. Other questions from this particular paper, this S1 paper, can be found in the link. If you click on the link over here, you'll find the playlist for the rest of the paper. If you click on the link over here, you'll find the playlist for questions dealing with histograms and these type of questions where we analyze the data, mean, standard deviation and skewness and whatever. And you can click on this link here to subscribe to the channel. Thank you for watching and see you soon.